What's up, everybody? I have a thing later tonight, so I was like, I'll do the officer. Apparently, I can't talk. I'm going to do the office hours earlier in the day. Oh my gosh. Let me send out a link. We're going to go here to Canvas. I'm getting choked up here. I feel like I moved the camera down a little bit, or I need to, I think, where is, or maybe, no, the camera can go down a little bit. I just need to sit straighter. That's what I need to do. That's what I need to do. And then we are properly framed up right here. We'll see if anyone joins the chat. We got to wake up MewBot. We'll say MewBot's not even here in the chat. Got to log into Canvas. Logging into Canvas Dual Mobile here. That was IUT before the Dual Mobile. Logging in. There we go. Getting logged in. No one's here yet. Let's say Chapter 7 homework. Who wants to do it? Let's say come complete Chapter 7 homework. Office hours live now. Completing Chapter 7 homework. Want to learn how to ace Chapter 7? Just click here. There we go. And we'll turn it into a link. Click here. A little chill music. Let's get started here. We'll see if anyone joins in. There we go. Link working. Link working. And now we publish. And we go there. And now we get ready to do some of the work. Let's do work. Work. No one's here yet. Besides me. So let's pull up the assignment. And let's do this. Okay, we got the homework going right here. We need to put the timestamps in the video. So here's the live stream. So if you're watching right now, you're going to see how to do the full assignment, starting with the first problem right here. So let's mark this right here on the time, 3:40:33, Stat Tool 1, Chapter 7 homework. Question 1. Let's do this. Okay, this first one right here is some true false, and we're going to go over the details of this. Some of the residuals. Here, let's grab this. We'll answer every question right here by looking at this and explaining it, because you don't want to just get them right. You want to know the answers and why the answers are the answers. It's one thing to get it right. It's another thing to know how to solve it. Some of the residuals from a least squares. Now, what does least squares mean? We don't really mention that much. It means when you have your dots and you add a line to it. So here's the line. This is the line of best fit. And what it does is, if you were to draw squares to the point, which if you go make a residual, that's a residual, which is the actual minus the predicted from the model. So the predicted, we maybe should do that in a different color. The predicted is going to be y hat. So that's from the model. There's not actually a point there. It's just the distance. And then the point itself is going to be the actual. And what we should probably do, make this even more clear, is the residual e is the distance right there. So residual e equals the actual, so equals actual minus predicted. That is residual. Residual equals actual minus predicted. So this would have a negative residual. And it says some of the residuals from the least squares linear model will be positive and some will be negative. This is true-ish. There is the point when they're all zero, if they're all on the line. They don't get into that specific case, so I get a little bit angry with this question, because there is the possibility that you could have a model where all the points are perfectly zero, and then that would mean there are no residuals. It should say if residuals exist, some will be positive and some will be negative unless they're all zero. That'd be more exact. We call it the least squares because when you calculate the total error, since some is negative and some is positive, I might not have drawn it all properly, but you can see there will be positive residuals. I'm doing them in green. To find out the total error here, what we do is we actually square this. And by squaring it, you make it positive. So you'd actually do what is called a sum of the squares. So if you were to do like a squared distance right here, you could turn them into squared residuals and then add up the squares. Like if that is negative 2 below. Yeah, Carson, because, and thank you, oh no, I'll be in person today. So I'm going to do the in-person. I just kind of got on here early. Let me look at my calendar, double check. In-person office hours, I got in here early. I won't be doing the online ones later because I am doing an event. So swing by the in-person office hours. Everything else is as normal. I just got on here early to do some of this. So we call this the least squares line. So this line right here makes the least squares, because if you were to change the line and be like, let's draw this line, well, then the square is going to be much larger. So now it's worse. Like, as in, we go back in time right here before we fit a line to it. And this is called the least squares line, because if you put in a line like this, which is actually more like a naive model, you're going to get big squares. And now there's a lot of error. Like, that's the residual, and then this is the square of it. So you'd get like a huge amount of error. And so we call it the least squares. Awesome, Carson. See you then. So the least squares line is the one that minimizes the sum of the squared residuals, the sum of the squared error. That's more detailed than we need to get into. But to know that some residuals are negative, which means they're below the prediction model, and some are positive, which means they're above the prediction model. And technically, to find out how much of the residuals they are, we can't just add them, because the sum of the residuals will add to 0, because some are positive and some are negative. They'd cancel out. So what do? We take the residuals, as I said, and we end up squaring the residual to make them all positive. So now it doesn't matter if it's below the line or above the line. We square them, and a positive 3 and negative 3 residual would both give 9 to the sum of the square error. So this is true. All that to say true. Least squares means that some of the squares of the residuals would be minimized. No, it means the sum of the square, the total. That's what the least squares line means. It means when you take your data and you fit a line, the line that makes the least squares is going to be something like this. There we go. It's going to be something like that-ish. It wouldn't be like these lines right here that I'm about to draw in red. It wouldn't be like this line or this line or this line. These are all horrible lines. The line that is the best line will minimize the sum of the squared error, not sum of the squared error. It should be the sum of the squared error. So that is false. When you write y hat, it denotes predicted, and that's what we said right here. We said y hat is coming from the line. So this comes from the linear model, the y hats. And then the dots themselves are the observed. So this is totally in line. And we should know that residual equals actual minus predicted right there. So good notes, that is true. So true, false, true. That's got the first question and a good review. So true and false, this means that the sum of the squares will be minimized. And then true right there. And once again, the best thing to do for these is if you know the answers without looking at them. Of course, we just kind of did a mini lecture on that, talking about even more advanced than we usually go in class, because we're not going to quiz you on the sum of the squared residuals. No one talks about that in business analytics. We talk about R squared, though. So we're going to talk about R squared probably later on, coming up here in a moment. Okay, we did question 1. So let's do question 2. Okay, question 2. A least squares regression model line was calculated to relate the length of newborn baby or boys, whatever, and we get this model. Now, here's the thing. If you get a regression model, you immediately want to write out what the equation you have is. Part of the class is understanding what you're seeing, and you might be familiar with the classic equation of y equals, I want a black pen, there we go, y equals mx plus b. Now, you can do it that way. You can do it that way, but we prefer in statistics to say y hat equals b0 plus b1x. Now, if you look, that makes b1 the m, that makes x the x.
Wow.
That makes b the b0, and y hat is the predicted. Very important that when you're talking about y hat, you're talking about the line of prediction right here, the line of prediction. That's what the y hat is. The y's in this are the actual dots, so the y hat is the prediction, and when you get y's, which are not the same as the other y, these are the actual values, the observed value. So if like this is someone making 100 on the test, this person made a 100, but you might have predicted they made about an 80, because they'd be on the prediction. Maybe they studied for like 2 hours. You're just doing like study hours and test score. So just a fake making up a problem. So we'd be predicting test score from study hours. So what do we have here? We are predicting a baby's weight, And then we have the intercept is negative 5.8. So if we're going to draw this model, let's do a quick sketch of it. And these steps really help you understand in detail what you're looking at. So don't skip these steps. Draw out what you got. Be like, let me draw it out. You know what I'm talking about. Draw it out. So we've got down here, the intercept is going to be at negative 5.38. Negative 5.38. That's where it would hit down here. So that is the intercept, the b or the b0. I prefer to do b0 plus b1x. The slope coefficient is going to be this. So that is going to be the rise over run. And the length is the x variable. That's the obvious one. That's the x variable of interest. The y variable. That's the explanatory variable. Don't listen to me. Don't listen to me. And this is the y variable of interest, the actual y variable of interest, which goes on the y-axis right there. The x goes on the x-axis. And the intercept we didn't color code down here. The intercept is that, and there's the intercept. So we could write the same thing below it, but I've already got it written above it. Just know that I'm using this equation right here, and it maps one-to-one color-coded with what you see. So that's what we got going on. So now let's see what it wants us to do. I think it wants us to predict. A newborn baby is 48 centimeters long and weighs 3 kilograms. So if the baby is 48 centimeters long, well, length is the x. So they're saying x equals 48. And then its weight, its actual weight, which is y, is equal to 3. Because that's its actual weight. When it says it actually weighs that, that is the observed. You see the baby weighs 3 kilograms. So then it says find its residual. So we need to take this value of x right here and plug it into the model to solve for the predicted. So that's going to use this line right here and predict. So maybe we should make it a little clearer that the model is giving the predictions. That is the name of the y variable, but the model is making predictions. It is the name of the y variable, but the model itself is making the prediction. So all we do is just take 48 and plug it in. You just go right here and you go 48. You say plug in 48. There's 48. So there we go. And let's do it. Now, this is not getting the residual. This is getting the predicted. So 48 times 0.1669, which is the slope, minus 5.38. And the residual is going to be 0.3788. Now, how did I know that? Well, this number, 6312, is y hat. Predicted weight is 6312. Y is going to be 3, which means the baby weighs 3. That's what it actually weighs. And it's predicted, if you went here to 2.6312, cannot write today, then this distance, residual equals actual minus predicted, we'll do this in orange, is how far away are those numbers. So you can kind of see visually, all you're going to do is subtract the numbers, and we need the value we have. So that's the, no, got it wrong. We don't have a color for actual. That's why I did that. So there's the predicted value from the model, predicted value, and the actual value. We'll do some purple. We'll circle it. It's a little, you can still see it, right? There we go, purple. And that's the actual. So that's the actual value right there. So when the baby actually weighs that. So all we do is subtract. So 0.3682 equals, we're just taking this equation, bring it here, 3 minus 2.6312. And so 3 minus that, and there it is. Oh, I was wrong on that. It's 88. I think I said that and then I wrote it wrong. There you go. 0.3688. That's how we do residuals. Actual minus predicted. Really? 3 decimals. When you try your best. And if you take a look, this will answer the question by looking at it visually. the baby weighs this much more than predicted because the residual is positive. When the residual is positive, the actual is higher than the prediction model. And so that means the newborn baby weighs this much more than predicted. There we go. Okay, let's do another. Where is it? Where is it? Look at this graph. Is that the right one? I think so. Okay. 1653. Let's do this question. If the correlation between two variables is positive, hello, good to see you there, Sham. If the correlation between two variables is positive, and Mubot says hi too, the slope of the linear model will be positive. I mean, we've been doing some tougher questions so far. This one's about as easy as it can get. I don't know if it's just this one question. If so, that's so nice. Because when you look at correlation, correlation tells you the direction. So because this has a positive correlation, R might be equal to something like 0.7. Well, then the linear model is going to be a positive slope, which is the rise over run. Whatever this rise over run is right here for each 1 unit increment of x. We expect y to increase by v1 on average. So I would say clearly yes, if the correlation is positive, and watch out, the trues and falses are flipped there, then yes. Well, man, that was easy. I wish they were all that easy. Now we get to a more difficult one. Okay, so let's do a tougher question. That one took less than a minute. So here is a more difficult question for us. Question number 4. Disk drives have been getting larger. The capacity are now in terabytes. 1 terabyte equals 1,000 gigabytes, or 1 trillion bytes. That's a lot of bytes. A survey of prices showed the data below, and let's take a look at it ourselves. Here we go. Okay, so what they're giving us right here, something's popping up. What's popping up down here? I'll do this later. Okay, cool. So what they're giving us is the data. Let's look at everything. We should know what all these things are. You ready? So here is the info on x, the x values, the y values. This is mean of variable y, mean of y. This is standard deviation of y. This is mean of x. This is standard deviation of x. And this is correlation, which is R, correlation. So we have all these values here. We've got tons of information on the screen, tons given to us. And so with this, what are they going to ask us to do right here? It says find the slope. Now, we can do this by hand. We have equations in the slides, or we can use the regression solver. Oh, we're doing regression right here, Sham. So this is linear regression. So, and check it out and ask questions if you got it. Good to see you here. And Mubot's in the class right now. Good to see you. So we are going to use, this is on our page right here. So we've got the Regression Solver Pro. So here's the Regression Solver Pro found under the modules. And all you do is you click in here to Regression Solver Pro. And then you download the Regression Solver Pro. And we're going to open up the Regression Solver Pro. I made this a while ago. Got to call everything Pro. Regression Solver Pro. And we're going to edit it. So here we go. We're going to bring this back over. How do we use the Regression Solver Pro? So now that you've got it opened up, take a look at what we got on the screen. There's 2 ways to use it. One, you can put the data inside of here. And this is a great question to show this off with. You can put the data in the X and Y fields, and it will be solved over here on the right. Or you can put in the summary statistics, like the slope, or well, not the slope, it'll solve the slope for you, which is the summary statistics. But right here is where you put in the values, like the value of correlation, the value of the standard deviation of y, and take it. Let's just do this right here. Let's go side by side screen right here. You ready? Okay, so watch this. Let's go. We're going to have to figure out how to get this all on screen one time. So you see, I'm going to put this right here. And then I go and say the correlation value is 0.987. The standard deviation of y is 141820. The standard deviation of x is 9.85. The mean of x is 7.611. The mean of y is 785.313. And now we get the value of the slope, which is right there, and the intercept. Notice everything's labeled in notation. You can also input values in here and it'll solve the regression equation for you, just like we were solving on the last question. Good to see you, Sham. And so now we're going to show how to use the other component of this. So we're going to go right over here and use the other component. So we're going to take the data and go right here, copy to clipboard. Now hit Command C, and then when you go inside or Control C on a PC, and then when you get over here into Excel, there we go. You want to paste it over to the side and figure out what is your Y variable of interest. Well, we want to predict the price of a hard drive, so we're going to copy this by, you can click and drag, a lot of people click and drag, and then hit Control C or Command C. Drop it right here. Do not overplace it on the Y. Don't place it over that. Drop it right there, paste, and then click the X variable, hold Shift and click the bottom one. Hit Control C or Command C, click the top cell, not the very top one, and then paste and look, do we get the same values? Even more decimal accurate. I don't know why Pearson's not carrying the decimals. If you put 200, you should get about the same predicted price. It's just that they're not carrying all the decimals. You know what this means now, though? We can just plug these numbers in. So when it says, what is the slope? We'll round to 2 decimals. We're just going to change this. Was that it? Is that all the decimals? Oh, it is all the decimals. Wow. So let's see. Which should round up right there. It's got some give on it. What does this mean? Well, we're predicting price. So for each additional terabyte, the hard drive is expected to cost about $1 more. Not $1, $142 more. And check this out. Slope. Newbot's going to say it in the chat. For each additional 1 unit increase in X, we expect Y to increase by B1 on average. So for each additional terabyte, we expect the hard drives to be about $142.11 higher. So it indicates the additional price for each additional terabyte in capacity. That should be good. Now we've got the intercept here, which is going to be illogical. It's negative. That's part of the reason it's illogical. Bring it down to 2 decimals. Round it, but there is a little bit of give on these questions. The intercept is the value of B0. And the intercept is when X is equal to 0, we expect Y to equal B0 on average. So think about this. When X, which is the capacity, when capacity is equal to 0, and you can see Mebot put it in the chat right there. When capacity is equal to 0, we expect the hard drives to be about negative $296.27 on average. Makes no sense. It indicates the price for a hard drive with no capacity is meaningless and shouldn't be interpreted. So now we have to write the equation. Well, we just kind of did this right here. I wish it's going to get mad if I don't round these. 142.11. This is B0 plus B1X. Just put the numbers correctly. What would you predict for a 20 terabyte hard drive? All you do is take your equation and just go right here and plug in 20. Let's go right here, plug in 20. And we should get about $2,400, which doesn't even make sense. Or you go back here and you just plug in 20. There you go. I was just guesstimating. Just plug 20 in and solve the equation, or take the number right there and solve. You just literally do 20 times this minus that. And now you can use the solver. I do suggest working some of these by hands. Nearest cent. Talking about cents like that, right? Of course. There you go. You find the 20 terabyte hard drive for $2,560, which is more than predicted. Just take a look right there. That is more than predicted. This would not seem like a good gut buy because the actual price is more than the predicted price. No, because the actual price is more than predicted. How much more or less is it? You're just literally going to take these two numbers and subtract them. What we've done right here in the previous part of the problem is we've found the predicted. This is y hat, and this is, you find it actually costs this. This is the y. So remember, residual equals actual minus predicted. So we're going to do the actual of 2560 minus the predicted of 2545. It's all right to write those eights. 2545.88 equals to the value of $14.12, I believe. $14.12. What's so interesting about these is I think there's so much of a give that I can just do this and you would pay this much more. And there is a little bit of leeway on these. Now, this is where students, just pause here before you click it. Please pause. A lot of people make a mistake right here. Does the model over or underestimate it? You got a 50-50 and you have to repeat this question if you mess it up. Now, you have to watch out because your question could be different. So remember, the residual is positive. The residual is positive. So that means the line, this is the line, which is the prediction. This is the predicted value. And the actual value is going to be like that because there's a positive residual. Positive residual. So does the model over or underestimate it? The model's underneath it. If the residual is positive, the model underestimates it because the model is below it. So the model is underestimated. If the residual is negative, the model would overestimate it. So this point right here would be overestimated with a negative residual. And this point right here with a positive residual would be underestimated. So it's underestimated with a positive residual. I wouldn't memorize that. I would try to do it visually. I would try to draw it out. So negative residual, overestimated, positive residual, underestimated. So the model is underestimating the price. Oh, that's got it right there. That was a tricky one. Oh, we just got one more part. Oh, this one gets me every once in a while. So some of these are just nonsense. Some of these answers you can eliminate because they're nonsense. The model might not be accurate because it has a certain amount of points. Well, the model might not be accurate because there are more than 5 data points. That's ridiculous. More data points are going to lead to a more confident ability in the model. Less than 20 data points, well, sorry, veterinary research. A lot of veterinary research is done with small data sets, so you can use small data sets to make conclusions. The model is accurate because it has a very high correlation. No. It might be just, there might be a relationship to this one extreme outlier pulling the data in this direction. So the model might not be accurate due to an extreme outlier. That's going to be right there. The outlier might be pulling the data in a certain way. So you have to watch out. The other answers are kind of nonsensy. Like, the model might be accurate because it has more than 5 points. We don't usually say things like that. Oh no, I deleted my note. Okay, let's take a look. That's the big question. A lot of people get stuck on that one. 28, 4-3. Okay, which of these gives the biggest contribution to the sums of the squares residuals? When you hear residual, you should just think error. And residuals are how far these are away. So as you go up in capacity, what you notice right here is the residuals get really big around here. So if we were to draw the line, and then we were to think about these points, well, we'll put like where 1 is at, where 3 is at, and where 4. There we go. 1, 2, 3, 4. Capacity in terabytes, a 90 megabyte hard drive. I don't even know what Pearson's doing. Who knows what they're doing? So this one would be positive, 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 and then, oh, wait, oh, down, oh my gosh, okay. Well, then apparently this one's negative. Oh, no, that's huge positive. What am I doing? This one's huge positive. I'm talking about this one right here. That one's huge positive, which I might not have put perfectly, which should be something in there. Huge positive, just as big negative, another big negative one at 3, somewhere in there, and then a positive one over here. This is a ridiculous model. Okay, there we go. So what I'm pointing out is this is what it would look like. So this one right here is that positive 5. It's 5 above the model. This one's the negative 18. I didn't draw that perfectly. It's negative 18 below the model. This one is the negative 19. It's negative 19 below the model. And this one is the positive 21. It's 21 above the model. And if you did the sum of the squared error, it would make the biggest square. As best I can draw, if you notice, like if we compare this to another one, it's not going to make as big of a square. And I might not have drawn these perfectly, but the one that's going to make the biggest sum of squared errors is just going to be the one that is the biggest when it comes to residual, because when you square everything, they all become positive. So the one that contributes the most is going to be the 0.31 terabyte hard drive. The sign of this wouldn't matter right here. A negative residual means that the drive, and let's take a look at our drawing, see how these... A negative residual is going to be like this green one right here. This is a negative residual. This is a negative residual. This is the predicted model right here. So it would mean it costs less than predicted. A negative residual means that the drive costs less than predicted and might be expected from a capacity of this amount. A residual of negative 19.44 indicates that the drive costs this many dollars less than expected because we're predicting the price from the capacity. Here we are with R squared. R squared is the percent of variation. Let me put the note for the question. R squared is the percent of variation in Y explained by the variation in X. So R squared is the percent of variation in Y explained by the variation in X. And here we'll put MuBot saying that in the chat. And let's take a look what they got going on right here. So you work at a store and you want to figure out your sales. Sales would be the variable of interest, and you'd want to use workers to explain it. So workers explain sales. Let's take a look. R squared is blank percent. So you take the correlation and you square it. That makes it positive. R squared is not correlation. That's a huge note to take. If you like taking notes in these videos, you write down R squared is not correlation. It is something actually called the coefficient of determination. And so it can only be positive because think if this was negative, if we had here negative 0.963 and it was negative, well, when you square it, it's going to be positive no matter what. That's because R squared tells us how much variation is explained, and explaining variation is a percentage out of 100. So 92.7% of the variation is explained of how much we sell based on who's working. Times it by 100 to turn it to a percentage, 92.74 or around there. And now we have to make sure we get just how it is. If I was doing this myself, I'd say 92.7% of the variation and how much we make is explained by our workers. So blank percent of the variation in sales is accounted for by a regression model of sales on number of salespeople working. And I don't love the way they phrase this. They're saying a model of Y based on X. So what is the percentage of the variation in Y that can be accounted for in a regression model of Y on X? So did I not do the rounding? Is the percent of variance in sales that can be accounted for by the regression model of sales. Something seems off. I feel like I got it right. Where did I make the error? 92.7. Round to one decimal. Let me double check the numbers here. I rewind time. I entered 963, which was something from earlier. 961. 92.3. 92.4 when you round. So how far off was I? Because it'll take that now. There we go. I was like something. Well, I should have checked. But 92.4, if you rewind the video, I entered 0.963, a number from earlier, 369. I reversed it. We had that in the math thing, and it was like question 2 or so. And so I entered that, and that's how I got the wrong value of R squared by using the wrong value of R. It should have been 0.961. Square that, and there's R squared. Coefficient of determination, percent of variation Y explained by the variation X. They say a model of Y based on X. Sure. Last question. Ooh, hope everyone's having a great day. 34:53. Last question of the homework. If our data is straight enough, we can model our data with a what? You should get this right away. This is QQ straight enough. No outliers. Plot doesn't thicken are the forward conditions for regression. So when we say our model is straight enough, we can model it with a line. That's what we're trying to do. The linear model, and that's got it. Well, maybe I'll put here chapter 7 homework. I might have time. We'll see if I don't know if I have 4 to 5 off today. We'll look at that. I'm going to answer some emails. Until then, bye for now, everyone. Let me change the outro. Closings, outros, Marvel quick. Wrong one. I got to take off video. Bye for now. Bye.